of experiments or what we can do with it. So we had 3 experiments. This is our potential vorticity. Zeta is absolute vorticity of planetary vorticity. So this is whole is potential vorticity. H over R is height of the water column, and it's depending on R. So this is what it creates for us topographic beta effect. And here is the result. Okay, this is a 4th sector. It's 90-degree sector. You can see that the center of the tank rotates this way, so it emulates the rotation of Earth. So this is west, and this is east. The jet goes this way. It's instantaneous picture, so you can see it goes like Florida loop current, and you can see the eddies here. It's actually very interesting that you can see it. Of course, it's not exactly the analogy because loop current goes the other way, but you can see that it has a tendency to be squeezed between eddies, and eddies also go this way. And if you average this picture in time, then all the eddies disappear and you only see alternating zonal jets. There is a discussion in the literature, do we have eddies or jets in the ocean, and what is striation, and what is all this? It all is concerned about the time, the time scale of measurement, because if you do it on short time scales, you will see a bunch of eddies. If you average, you will see jets. So there is no contradiction here. You just need to agree what you study, and you need to define parameters which determine the different regimes. Now, we computed the spectra. So this is the zonal spectrum and non-zonal spectrum. Like on Jupiter, you can see that the zonal spectrum goes with a slope of n to minus 5 in all 3 experiments. Non-zonal spectrum goes with a slope of minus 5/3. So this is also like on Jupiter, which is pretty amazing. Of course, you can tell me that it's all nonsense because I don't even have a decade in the wave numbers. But I'll tell you that I can't have any better because my forcing is here. This device is too small, and I work with what I have. I just cannot improve it. However, we have now another project which is approved, a much bigger device. It's 6 meters in diameter in University of Torino, and we do it in collaboration with people in University of Torino and people in University of Oxford. And we're going to go to Torino sometime early next year, and we're going to repeat the whole thing in much bigger device. Hopefully, we shall have more convincing results. But for the time being, we see that like on Jupiter, we have minus 5/3 for non-zonal spectrum, minus 5 for zonal spectrum. Coefficients are very close to what we measure in Jupiter. So to some extent, we can reproduce Jupiter circulation in very small device. And, we are comparing 70,000 kilometers in radius for Jupiter with 60 centimeters in diameter for the whole thing. Now, we look now on PV monotonizing. This was our idea. So this is a snapshot of the velocity in 3 experiments. It's a zonal velocity. You see this jet goes to the west. And this is instantaneous potential vorticity profile. So unlike we used to think that it's almost constant, it's not constant at all. It's very inhomogeneous. And if you compute the derivative of this profile with radius, dq by dr, this is what is called the Charney-Stern stability criteria. The flow is unstable when the derivative crosses 0. So you can see it here. It does cross 0 quite a lot. So the flow is barotropically unstable. If you take a monotonic vorticity profile, the thing will be stable. You will not get any turbulence in it. So this is what happens after monotonizing. This is monotonized potential vorticity, and this is non-monotonized potential vorticity. So after monotonizing, you don't have any turbulence. It's all stable. And of course, you don't have any turbulence. So if you think that you can study this kind of flows by monotonizing potential vorticity, you are going to miss turbulence. You are going to miss mixing. You are going to miss a lot of physics. And by the way, it holds true for atmospheric jets, for ACC, for planetary jets. This is a very important point, that we shouldn't be working with fully monotonized or homogenized vorticity. We need to look into variation with time. And what we found that we can compute this scale LM by monotonizing potential vorticity profile. And we can have different ways to do it. We can average in time, we can average in space. And it seems to be related to L beta, which we know because epsilon is known, we can measure it, by a relationship Lm is equal to 4.5. So not only we can define this new length scale and compute it, but it seems to be kind of solidly related to L beta. So this is analog of the Thorpe scale for planetary jets. And it's very useful because it gives us a possibility to compute the rate of inverse cascade without computing the spectra. So this is, hopefully this method will attract attention and people will start using it. And as I said, now we studied the jets which go to the west. Now we have a new series of experiments of the jets which go to the east. And the same thing seems to be working for them as well. And they're even more important because most of the jets which we deal with in our environment are eastward. Now, this is what happens when you plot the map of particle trajectories converted into final size Lyapunov exponents. It's a way to study dispersion between the particles. It's how distance between the particles grows with time or with, well, let's say it's with time. It's a little more involved than this. This is a forced sector. The jet goes this way. And so you can see that there is a lot of dispersion over the jet when the forcing is present. When it's not present, the dispersion reduces, but it's still large in both tongues. And the middle place seems to be smaller dispersion. So people talk about the barriers to the mixing. So this middle of the jet seems to be a barrier to the mixing, particularly when the forcing is absent. It's strange to see it, and I think that the reason for it is the presence of the eddies. The eddies make the potential vorticity profile more unstable, and they create excessive mixing. They enhance mixing. But when you go out of the forced area, obviously they decay and the mixing falls, and there's, in the middle there's actually the mixing itself is proportional to epsilon. So when epsilon goes to 0, the mixing will go to 0 as well. We can, by this, this is what we see here is it's more than just a picture, because the way the final scale Lyapunov exponent depends on the separation. It determines the diffusion regime. It may be Richardson diffusion regime or Taylor diffusion regime. One is has variable diffusivity, and the Taylor is constant diffusivity. So from looking in this picture and doing some analysis, you can actually see what kind of diffusion regime is there. And this picture can be almost directly transferred to oceanic and atmospheric jets, and this is our next step. This is actually the subject of the next paper to GRL, and it has a lot of different applications later on. Just I'm going to conclusion. Monotonizing of potential vorticity in geophysical flow produces a length scale which is analogous to the Thorpe scale, and we establish the coefficient of proportionality, which is most practically important. From this scale, we can estimate the rate of inverse cascade directly from limited amount of data. What is interesting is that the energy which is released by monotonizing potential vorticity can be estimated by this expression. If you look at it, this is like kinetic energy of rotating body. It's momentum of inertia times omega square. We have omega square here, and the rest is like equivalent moment of inertia of turbulence scales in this rotating body. The models which use perfect potential vorticity staircases which are stable by Charlie Stern, they miss the effect of turbulence. And again, as I said, LM, this analog of the Thorpe scale, can be used to diagnose geophysical and planetary macroturbulence. And it can be used for diagnosing time and time and space variability and the energetics of those flows. And I'm done.